Hey guys, today we're going to learn about components of weight, or more specifically, how we deal with masses that are sitting on slopes and figure out how much weight is dragging them down the slope and how much weight is actually pushing them into the slope. So to get there, we're going to do a quick review of Sohcahtoa because everyone loves Sohcahtoa. We'll do another brief review of breaking vectors into components, which is a general skill that we learned before. And then we'll get to the heart of the matter, which is dealing with masses on slopes. Now we're going to need to go to the document camera for this one, so here we are. Okay, so Sohcahtoa, it's a mnemonic to figure out the trigonometry of things and remember the trigonometry of things. So we have a right triangle with an angle theta that we are interested in. We have the adjacent side, that's the side adjacent to our angle, the opposite side, opposite our angle, and the hypotenuse. And the mnemonic says the sine of theta, the sine of this angle, is equal to the opposite over the adjacent. That's the opposite over the hypotenuse. That's the O, the H. Cosine theta is the adjacent over the hypotenuse, and the tangent theta is the opposite over the adjacent. Now today we're going to be mainly using just these two, the sine and the cosine functions. So now we're going to briefly review how to break vectors into components, which we've seen before. So imagine we have a vector like this, okay? So it's some vector quantity going down at an angle like this, and we're going to call this angle here theta. And what we want to figure out is what the vertical component is, the y component, and the x component. Okay, now we're going to say this is 50 degrees. Okay, and we're going to say that the length of the hypotenuse we'll say is 15. And we want to figure out the length of y and the length of x. And we use Sohcahtoa to do this. So we're going to do both. We're going to do the sine of 50 degrees is equal to the opposite over the hypotenuse. So that's going to be x over 15. And then we can break that down into 15 times the sine of 50 degrees is equal to x. And then 15 times the cosine of 50 degrees is going to be y, because the cosine of 50 degrees, cosine of the hypotenuse, is equal to the adjacent, which is y over the hypotenuse. Okay, so the cosine of 50 degrees, cosine of theta, is equal to the adjacent over the hypotenuse. Okay, now I've got my calculator out, so we'll be able to do this math. So we're going to do the sine one first. So 50 degrees, take the sine of it. We're going to multiply that by 15, and that equals 11.5. Pretty close. That's the x. And then same thing for the cosine. We're going to do 50 degrees, take the cosine, times 15 equals 9.6. Right? So we now know that this equals 9.6, this equals 11.5. Now I didn't draw the triangle exactly to scale, but we know that this is greater than 45 degrees, so we would expect this leg to be longer than this one. So 11.5 and 9.6. Okay. Let's do one more here. Let's say we've got, let's call this 70 degrees, and we're going to call this 15 again. 15 units. And we want to know the y component and the x component. So we're going to do 15 times the sine of 70 degrees and 15 times the cosine of 70 degrees. Let's see, get it out of the glare there. So 70 degrees sine times 15 equals 14. I'm going to do that again because I hit a wrong button and I don't want to confuse you. 70 sine times 15 equals 14.1. Now we do same thing with the cosine. 70 degrees, take the cosine times 15 equals 5.1. Okay, now you notice I've done both functions, the sine and the cosine. And then once I have the numbers, then I'm just going to put them in. 14.1 for the long side, 5.1 for the short side. For most of these problems that we're going to be doing, you're going to be doing both the sine and the cosine. And just speaking for myself, I find this easier to just do them both and then put the numbers where it makes sense that they would go. Okay. So yeah, so that's our review of how we figure out the components. So what we've done here is we've been given a vector which is coming down at some angle, and we figured out the vertical and the horizontal components of it. We're going to be using that as we move forward. Okay, so let's go back to our slide presentation here, and we're going to look at this blow up. There we go. Okay, so this looks a little complicated, but bear with me. It's not as scary as it looks. What we have is a ramp, and the ramp has a slope on it of some number of degrees. So that's what this theta is here, is the angle above horizontal. And we have a mass, and we know what that mass is. To keep it from being cluttered, I haven't put a number in for this one, but yeah, we know that there's a mass for it. So now the weight produced by that mass, in other words, the force of gravity on that mass acts straight down, and that's that straight down vertical vector of F sub g. So the weight of the mass is going straight down. It's being attracted to the center of the earth. And what we want to do is figure out what the components of that weight are that are trying to drag the thing down the slope, and what the component is that is kind of driving it straight into the ramp. Okay, so if we take the, we put another vector up this way. There's a vector working up in this direction, which should have an arrowhead on it. Let's try that again. Put an arrowhead on this. There's a force vector acting on the mass, which is the normal force. It's the force applied by the ramp itself, which, as you recall, normal force acts perpendicular to any surface. So the slope here has the weight sitting on it, and the normal force is pushing the mass up and to our left as we look at this diagram here. Okay, and that is the normal force. We could even label that in here as F sub n if I was able to write on this, but I can't. So this is the normal force. And third law tells us that the normal force has to be equal to the force that the mass is exerting against the surface. So we are going to break this. I'm going to move this away here so we unclutter it again. Okay. All right. So we have our force vector, the weight of the block, which is pulling straight down. And there is a component of that force which is down the slope, and a component of that force which is into the slope. And we are going to readjust our axes a little bit so that x, instead of being horizontal, is straight down the slope, and y, instead of being straight down, is straight into the slope. So they're at 90-degree angles from each other. Fgx is the force of gravity acting down the slope, and Fgy is the force of gravity acting into the slope. They're the components. Now, what we can see here, and what I have written in red, is that if you add the y vector and you add it to the x vector, you will get the weight vector. So the weight vector is made up of two components, the y component and the x component. And if we know this angle here, we can figure out the magnitude of the downslope force and the into the slope force, the x component and the y component. We do it exactly the way we just did in the example that we had there. Okay, so the last little piece here is, well, what's this angle? Well, this angle at the apex of this right triangle is the same as this angle of the slope of the ramp. Okay, so now we're going to do some math problems with masses on slopes to figure out the downslope force, that's Fgx, and the into the slope force, which is Fgy. Right? And the way we're going to do this is we have a 0.5 kilogram mass on a 35-degree slope. So we're going to do, first we're going to convert these into newtons. Sometimes you need to do this and sometimes you don't. So we're going to do this first. 0.5 kilograms times 9.8 meters per second squared is equal to 49 newtons. 49 newtons. Okay, so this is the force of gravity, in this case, is equal to 49 newtons. Now, what we're trying to do is figure out for our weight, which is 49, we're trying to figure out the component which is into the slope and the component which is down the slope. This is FGX, this is FGY, not necessarily drawn to scale. And our angle here is 35 degrees. So we're going to do both the sine and the cosine feature of this. So we're going to say 49 times the sine of 35 degrees, and we're going to do 49 times the cosine of 35 degrees. So 35 sine times 49 equals 28.1 newtons, and 35 cosine times 49 newtons equals 40.1 newtons. All right, now we can tell by looking at this that since we're relatively flat, we're flatter than 45 degrees. That means that the weight down is going to be greater than the weight, or the weight into the slope is going to be greater than the weight down the slope. So this is f of x, FGX, and this is FGY. Okay, so this is this component, and this is this component. So we come up with 28.1 and 40.1 newtons. All right, now, since that is the weight into the slope, that is also the value of the normal force. So the normal force is also equal to 40.1 newtons. Okay, that's that. Now let's do another one. This is a much steeper slope, 70 degrees, but it's still 0.5 kilograms. So it's still 49 newtons. What we're trying to figure out here, that's F sub G, and we know that that is 49 newtons. And we want to know this component, that's FGY, and this component, which is FGX, FGY, right? This is our right triangle. This has to be 70 degrees, because that's the same as this one here. We were using 35 degrees on this one here, because this angle here was 35 degrees, right? So we're going to wind up with 49 times the sine of 70 degrees, and 49 times the cosine of 70 degrees. 70 sine times 49 equals 46 newtons. Oops, how about 70? There we go. Cosine times 49 equals 16.8 newtons.